In 1916, a German astronomer named Karl Schwarzschild sat in the trenches of the First World War and solved one of the most difficult equations in the history of physics. Working from Albert Einstein's freshly published theory of general relativity, Schwarzschild calculated exactly what would happen if you compressed all of an object's mass into an impossibly small point. The answer Karl Schwarzschild found was absolutely and completely terrifying. Space itself would curve so violently that nothing, not matter, not radiation, not even light, could ever escape. He had described, mathematically, the first black hole. More than a century later, the James Webb Space Telescope has discovered black holes so enormous, so impossibly early in the history of the universe that they are breaking the very models we built to explain them. This is the story of the too big, too fast problem, and it may force us to rewrite everything we thought we knew about how the cosmos assembled itself. Let us start from the ground up and define, in plain English, what a black hole actually is. A black hole is a region of space where gravity has become so overwhelmingly powerful, that the escape velocity, the speed you would need to travel to break free, exceeds the speed of light. And because nothing in the universe can move faster than light, which travels at exactly 299,792,458 meters per second, for a non-rotating black hole, the radius of the event horizon is given by the Schwarzschild radius formula, r equals 2 times g times m, divided by c squared. A stellar mass black hole containing 10 times the mass of our Sun has a Schwarzschild radius of just 29.53 kilometers. That is roughly the width of a single city. You could drive across the event horizon in about 20 minutes. But a supermassive black hole weighing 50 million solar masses, like the one recently discovered in the object known as QS01, commands a Schwarzschild radius of nearly 148 million kilometers. That is 0.987 astronomical units. Its event horizon would stretch almost from the Sun to the orbit of Earth. Nothing escapes past that boundary because, beyond it, space-time itself is curved so steeply. It is not that the gravity is simply strong, it is that the geometry of space has been rewritten. The first category is stellar mass black holes, weighing between 5 and 100 times the mass of the Sun. These are the collapsed remnants of massive stars that have exhausted their nuclear fuel and undergone gravitational implosion. The most famous example is Cygnus X1, first detected in 1964 by a rocket-borne Geiger counter that picked up its intense X-ray emissions. It was confirmed through optical telescopes in 1971 and has a measured mass of 21.2 solar masses. Cygnus X1 sits roughly 6,000 light-years from Earth, making it one of the closest known black holes to our solar system. The second category is intermediate mass black holes. These are the middleweights, ranging from 100 to 100,000 solar masses, and and they are the rarest and most elusive class. For decades, their existence was debated. The merger of two black holes that produced a final remnant weighing 142 solar masses. But Sagittarius A star is a relative lightweight, 53 million light-years away. At the core of the giant elliptical galaxy Messier 87 lurks M87 star. Weighing 6.5 billion solar masses, it was the first black hole ever directly imaged in 2019. And at the extreme end of the scale sits TON 618, a quasar-powered ultramassive black hole estimated at roughly 66 billion solar masses. One of the most massive black holes known in the observable universe. Now, matter rarely falls straight into a black hole because everything in the universe carries some amount of angular momentum. Incoming gas and dust do not plunge in directly. Instead, they spiral. Imagine water circling a bathtub drain. The material flattens into an intensely fast-moving disk of superheated gas called an accretion disk. In this disk, the inner lanes are screaming around the black hole at significant fractions of the speed of light, while the outer lanes orbit more slowly. This enormous difference in velocity causes adjacent layers of gas to grind against one another, generating extreme friction. That friction strips electrons from atoms, turning the gas into turbulent plasma and heats it to temperatures reaching millions of degrees. At these temperatures, the accretion disk blazes with optical light, ultraviolet radiation, and ferocious X-rays. A black hole, paradoxically, becomes one of the most luminous objects in the universe, not because anything escapes from within, but because the process of falling in converts gravitational energy into radiation with extraordinary efficiency. Many actively feeding supermassive black holes also launch relativistic jets, twin beams of superheated plasma fired outward from the rotational poles at nearly the speed of light. These jets can extend for hundreds of thousands of light years, dwarfing the galaxies that produce them. With that foundation laid, we can now address the central question of this video: how fast can a black hole grow? The answer is governed by a principle called the Eddington limit, named after the British astrophysicist Arthur Stanley Eddington, who described it in 1926. The Eddington limit is the fundamental speed limit on black hole growth. Here is how it works. As an accretion disk devours matter, the extreme friction causes it to radiate intensely. Light is made of photons, and photons carry momentum. They push. If a black hole consumes matter too quickly, the brilliant radiation generated by its accretion disk pushes outward harder than the black hole's gravity pulls inward. Think of it like eating a chili pepper so unbearably hot that the burning forces you to stop eating and gasp for air. The outward blast of radiation literally blows the black hole's food supply away, halting growth until the surrounding environment cools down and matter can begin falling in again. The luminosity at which radiation pressure perfectly balances gravitational attraction is the Eddington luminosity. It is directly proportional to mass. The more massive the black hole, the higher the luminosity it can sustain before blowing its food away. For a 100 solar mass black hole, the Eddington luminosity works out to approximately 1.26 times 10 to the 33rd watts. That is about 3.28 million times the luminosity of our Sun, generated by a black hole that is, cosmically speaking, tiny. Because this speed limit is fixed by physics, black holes can only increase their mass at a defined maximum rate. The time it takes for a black hole to double its mass while feeding continuously at the Eddington limit is called the E-folding timescale. Assuming standard thin disk accretion with a 10% radiative efficiency, one E-folding takes approximately 45 million years. This number is absolutely critical, so let us run the math on what it means for the early universe. Imagine a black hole seed is born with a mass of 100 solar masses. That is a perfectly reasonable starting point for the collapsed remnant of a massive first-generation star. Now give it the most generous possible conditions, continuous, uninterrupted feeding at the absolute maximum Eddington rate, with no breaks, no disturbances, no mergers needed, just pure, constant growth. To grow from 100 solar masses to 1 billion solar masses requires about 16.1 E-foldings. At 45 million years per E-folding, that demands roughly 725 million years. The leading explanation for how jets form is the Blandford-Znajek mechanism, first described by Roger Blandford and Roman Znajek at Cambridge in 1977. In simple terms, a spinning black hole drags the fabric of space-time around with it. The accretion disk is threaded with powerful magnetic field lines, and these field lines get caught in the rotating spacetime. The black hole twists them into a tightly coiled vertical funnel. The magnetic tension becomes so extreme that it acts like a cosmic slingshot, extracting rotational energy directly from the black hole itself. And channeling incoming plasma outward along the poles before it ever crosses the event horizon. With that foundation laid, we can now address the central question of this video: how fast can a black hole grow? The answer is governed by a principle called the Eddington limit, named after the British astrophysicist Arthur Stanley Eddington, who described it in 1926. The Eddington limit is the fundamental speed limit on black hole growth. Here is how it works. As an accretion disk devours matter, the extreme friction causes it to radiate intensely. Light is made of photons, and photons carry momentum. They push. If a black hole consumes matter too quickly, the brilliant radiation generated by its accretion disk pushes outward harder than the black hole's gravity pulls inward. Think of it like eating a chili pepper so unbearably hot that the burning forces you to stop eating and gasp for air. The outward blast of radiation literally blows the black hole's food supply away, halting growth until the surrounding environment cools down and matter can begin falling in again. The luminosity at which radiation pressure perfectly balances gravitational attraction is the Eddington luminosity. It is directly proportional to mass. The more massive the black hole, the higher the luminosity it can sustain before blowing its food away. For a 100 solar mass black hole, the Eddington luminosity works out to approximately 1.26 times 10 to the 33rd watts. That is about 3.28 million times the luminosity of our Sun, generated by a black hole that is, cosmically speaking, tiny. Because this speed limit is fixed by physics, black holes can only increase their mass at a defined maximum rate. The time it takes for a black hole to double its mass while feeding continuously at the Eddington limit is called the E-folding timescale. With that foundation laid, we can now address the central question of this video: how fast can a black hole grow? The answer is governed by a principle called the Eddington limit, named after the British astrophysicist Arthur Stanley Eddington, who described it in 1926. The Eddington limit is the fundamental speed limit on black hole growth. Here is how it works. As an accretion disk devours matter, the extreme friction causes it to radiate intensely. Light is made of photons, and photons carry momentum. They push. If a black hole consumes matter too quickly, the brilliant radiation generated by its accretion disk pushes outward harder than the black hole's gravity pulls inward. Think of it like eating a chili pepper so unbearably hot that the burning forces you to stop eating and gasp for air. The outward blast of radiation literally blows the black hole's food supply away, halting growth until the surrounding environment cools down and matter can begin falling in again. The luminosity at which radiation pressure perfectly balances gravitational attraction is the Eddington luminosity. It is directly proportional to mass. The more massive the black hole, the higher the luminosity it can sustain before blowing its food away. For a 100 solar mass black hole, the Eddington luminosity works out to approximately 1.26 times 10 to the 33rd watts. That is about 3.28 million times the luminosity of our Sun, generated by a black hole that is, cosmically speaking, tiny. Because this speed limit is fixed by physics, black holes can only increase their mass at a defined maximum rate. The time it takes for a black hole to double its mass while feeding continuously at the Eddington limit is called the E-folding timescale. Assuming standard thin disk accretion with a 10% radiative efficiency, one E-folding takes approximately 45 million years. This number is absolutely critical, so let us run the math on what it means for the early universe. Imagine a black hole seed is born with a mass of 100 solar masses. That is a perfectly reasonable starting point for the collapsed remnant of a massive first-generation star. Now give it the most generous possible conditions, continuous, uninterrupted feeding at the absolute maximum Eddington rate, with no breaks, no disturbances, no mergers needed, just pure, constant growth. To grow from 100 solar masses to 1 billion solar masses requires about 16.1 E-foldings. At 45 million years per E-folding, that demands roughly 725 million years. This timeline seems long, but workable until you realize that the James Webb Space Telescope has found supermassive black holes operating when the universe was only 500 million years old. At 500 million years, you can fit at most about 11 E-foldings. 11 E-foldings starting from 100 solar masses gives you a maximum mass of roughly 6.7 million solar masses. That is a respectable black hole. But JWST has found black holes at this epoch, weighing tens of millions to potentially hundreds of millions of solar masses. They are simply too big, too fast. The math does not work. Something is profoundly wrong with the standard picture. Now, there is a theoretical escape hatch called super-Eddington accretion under specific, extreme conditions when a black hole is engulfed by an overwhelmingly dense supply of pristine gas. Nantraripasuri, namaraver, nanur, nataraver, damburi, nabarakuri, nanaraver. The accretion disk can abandon its standard thin, flat shape and puff up into a thick, bloated structure called a slim disk. In this swollen configuration, the infalling gas is so dense that it physically traps the outward-pushing photons. The light cannot fight its way through the dense traffic of gas fast enough to blow the material away. Instead, the radiation gets dragged inward along with the gas directly into the black hole. Through this photon-trapping mechanism, theoretical models and advanced simulations suggest that a black hole can temporarily gorge itself at rates 2 to 10 times above the standard Eddington limit. Marek Abramovich and colleagues first described the slim disk model in 1988. Marta Voluntari and collaborators at the Institut d'Astrophysique de Paris explored its implications for early universe black hole growth in 2015, and Kohei Inayoshi at Peking University published updated subgrid models for super-Eddington accretion as recently as 2024. Super-Eddington accretion helps, but even at 10 times the Eddington rate, sustaining that kind of feeding frenzy continuously for hundreds of millions of years requires conditions so extreme and so specific that many astrophysicists remain deeply skeptical that it alone can explain what JWST is finding. Before JWST launched, the prevailing model for how supermassive black holes formed relied on what is called the light seed pathway. The idea was straightforward. The very first generation of stars, called population 3 stars, formed out of pure primordial hydrogen and helium roughly 1 to 200 million years after the Big Bang. Because this pristine gas contained absolutely no heavy elements, there was no efficient way for the collapsing gas clouds to radiate away heat. Without cooling, the clouds could not fragment into smaller pieces. Instead, they underwent monolithic collapse, forming singular, gargantuan stars, weighing between 100 and 300 solar masses. When these behemoths exhausted their fuel and died, they left behind stellar mass black hole seeds weighing 10 to 100 solar masses. According to the pre-JWST consensus, these light seeds would then spend the next several billion years slowly growing through sustained accretion and occasional galactic mergers, eventually becoming the supermassive black holes we observe in the centers of mature galaxies today. It was a tidy, elegant model, and then JWST looked at the infant universe and broke it. In 2023, JWST identified CEERS 1019, an actively accreting supermassive black hole with a mass of approximately 9 million solar masses. Its redshift of 8.7 places it at a time when the universe was only 570 million years old. In 2024, the telescope confirmed GN-Z11, a vigorously feeding black hole of 1.6 million solar masses at a redshift of 10.6, corresponding to just 420 million years after the Big Bang, deep within the cosmic dawn. And perhaps most strikingly, JWST and the Chandra X-ray Observatory together identified UHZ1, a black hole estimated at 10 to 100 million solar masses at a redshift of approximately 10.1, just 470 million years post-Big Bang. In UHZ1, the black hole's mass was comparable to, or potentially exceeding, the entire stellar mass of its host galaxy. That had never been seen before. The timeline simply does not accommodate the light seed model. At 500 million years, even perfect Eddington rate accretion from a 100 solar mass seed can produce at most a few million solar masses. Finding black holes of tens or hundreds of millions of solar masses in this window means that either these black holes were born already massive, bypassing the light seed stage entirely, or they somehow sustained super-Eddington accretion for the majority of their existence without interruption. And then, in 2025, the problem got worse. The JWST Capers program discovered Capers-LRD-Z9, a compact gas-enshrouded galaxy hosting a broad-line active galactic nucleus at a confirmed redshift of 9.288. That places it barely 500 million years after the Big Bang. Its central black hole weighs approximately 38 million solar masses. Its host galaxy contains less than a billion solar masses of stars. It is another impossibly overmassive system, another black hole that has no business being that large, that early, under any standard model of cosmic growth. So, if light seeds cannot explain these objects, What can? Astrophysicists have developed three competing theories for how supermassive black hole seeds might form. The first is the light seed model we have already discussed, population 3 remnants weighing 10 to 100 solar masses. This pathway was described in foundational work by Tom Abel, Greg Bryan, and Michael Norman in 2002, and by Volker Braun and Richard Larson in 2004. It remains the most physically straightforward mechanism, but it fundamentally struggles with the JWST timeline. The second theory is the heavy seed pathway, also known as the direct collapse black hole model. In this scenario, black hole seeds skip the stellar phase entirely and are born massive in the range of 10,000 to 1 million solar masses. The mechanism requires very specific conditions. A pristine, metal-free gas halo, typically weighing 10 million to 100 million solar masses, must be bathed in a strong flux of Lyman-Werner ultraviolet radiation from a nearby star-forming galaxy. This specific wavelength of radiation destroys molecular hydrogen, which is the primary coolant in metal-free gas. Without cooling, the gas cannot fragment into individual stars. Instead, the entire cloud undergoes a catastrophic, monolithic collapse, either forming a supermassive protostar that rapidly implodes under its own weight, or plunging directly into a massive black hole. Mitchell Begelman, Marta Voluntari, and Martin Rees described this mechanism in 2006. John Wise and colleagues at Georgia Tech demonstrated it in detailed simulations published in Nature in 2019. Heavy seeds elegantly solve the JWST timeline problem because they start life already enormous. But the conditions required to form them, a metal-free halo with just the right Lyman-Werner flux at just the right distance from a neighboring galaxy, are thought to be extremely rare. The third and most exotic theory involves primordial black holes. Unlike light or heavy seeds, primordial black holes do not require the collapse of gas or stars at all. They formed during or immediately after the Big Bang itself. During the rapid expansion of cosmic inflation, quantum fluctuations in the density of the universe were scattered across space. If a localized region happened to be sufficiently overdense, the ambient pressure and gravity would cause that patch to collapse directly into a black hole before any stars or galaxies had even begun to form. The theoretical groundwork was laid by Yakov Zeldovich and Igor Novikov in 1966 and extended by Stephen Hawking in his landmark 1971 paper and by Hawking and Bernard Carr in 1974. Primordial black holes remain highly speculative. And current observational constraints from the cosmic microwave background and gravitational microlensing surveys have ruled them out in many mass windows, but they have not been conclusively eliminated in all mass ranges. And notably, the 2026 JWST measurements of the QSO-1 system found black hole to galaxy mass ratios that the research team described as consistent with primordial black holes. Now, there is a critical piece of this puzzle that ties everything together, and it is something JWST discovered that nobody predicted. They are called little red dots. Little red dots are an entirely new class of astronomical object, first identified and named by astronomer Jorit Mathie and his team in 2024. Their spectral energy distribution has a distinctive V-shape, dim on the blue side, sharply rising into the red. When astronomers obtained spectra of these objects, approximately 80% of them revealed extremely broad hydrogen emission lines, the classical signature of gas orbiting at thousands of kilometers per second around a central supermassive black hole. To date, JWST has identified hundreds to well over 1,000 of these sources scattered across the early universe, making them far more abundant than anyone anticipated. The defining mystery of little red dots is what researchers call the overmassive black hole problem. In a typical galaxy in the nearby universe, the central black hole accounts for roughly 0.1% of the galaxy's total stellar mass. It is important, but it is a tiny fraction of the whole. In little red dots, the black hole appears to make up 10 to 100% of the entire system's mass. The black hole is not a small engine at the center of a large galaxy. The black hole is the galaxy, or very nearly so. This has ignited a fierce debate. If the broad emission lines in little red dots are genuinely produced by accreting supermassive black holes, then why are these objects so faint in X-rays? Active galactic nuclei of this mass should be screaming in X-rays, and yet many little red dots are essentially invisible to X-ray telescopes. Fabio Pacucci and Ramesh Narayan at the Harvard-Smithsonian Center for Astrophysics have proposed that mildly super-Eddington accretion onto slowly spinning black holes could explain this X-ray weakness. Others have suggested that the broad lines might not come from black holes at all, but from extremely dense stellar outflows or runaway collisions in ultra-compact star clusters. However, if little red dots are purely stellar systems, the implied densities, 10,000 to 1 billion solar masses per cubic parsec, are so extreme that the stars would physically destroy each other through constant collisions. The reason little red dots matter so profoundly is that they appear to be the missing evolutionary link astronomers have sought for decades. We have long known about stellar mass black holes in our local neighborhood and about fully matured billion solar mass quasars in the distant universe. But the transitional stage between seed and giant was invisible. Little red dots appear to be that transition, seed black holes caught in the act of their earliest, most aggressive growth phase, dominating their host galaxies before those galaxies have had time to fully assemble. Let us take a step back and consider the historical arc of what we have learned. In 1916, Schwarzschild published his solution, and black holes became a mathematical possibility. In 1964, Cygnus X1 was detected, and they became an observational reality. In 1971, Hawking proposed that some might have formed at the dawn of the universe itself. Then, in 2019, the Event Horizon Telescope showed us the shadow of M87 star, and in 2022, it captured our own Milky Way's central black hole, Sagittarius star. With those images, black holes became things we could see with our own eyes. But then the James Webb Space Telescope opened a window to the infant universe that had never existed before. In 2023, CEERS 1019. In 2024, GN-Z11 and UHZ1. In 2025, CAPERS-LRD-Z9. Each discovery pushed the problem further. Each black hole was too massive, too early, too dominant over its host galaxy. And then, in May 2026, came the result that may have changed everything. The direct kinematic mass measurement of the QSO-1 system, published in Nature. For the first time, astronomers did not estimate a distant black hole's mass through indirect proxies. They measured the actual orbital velocities of gas swirling around it, and calculated the mass directly. The result confirmed a 50 million solar mass black hole that constitutes roughly 2/3 of its host system's total mass, observed at a time when the universe was barely 700 million years old. That measurement is what we will explore in detail in Part 2. Roberto Maiolino, the lead researcher at the Kavli Institute for Cosmology at Cambridge, described the finding this way. This is a remarkable finding. It is a paradigm shift, a total revisiting of the classical scenarios of how black holes form and grow. The undersciencer that beurtansers. His colleague, Ignace Juojbalis, added, "It seems that we have found a black hole that does not have a substantial host galaxy and that has predated stellar processes. This is very exciting because it is evidence for primordial black holes, or direct collapse black holes, which have been theorized but have not been confirmed." And Francesco D'Eugenio, also of Cambridge, emphasized what made this measurement fundamentally different from everything that came before. Before now, all of the mass measurements of black holes in the early universe have been indirect, based on assumptions from what we know about them in the local universe. We did not know if those assumptions really apply to the distant universe. What is unfolding right now is not merely a scientific update. It is a paradigm shift with direct historical precedent. In 1963, the astronomer Martin Schmidt analyzed the spectrum of a peculiar, star-like object called 3C273 and discovered that it was not a nearby star at all. It was an object billions of light-years away, blazing with the luminosity of an entire galaxy, powered by something pouring energy out of a volume no larger than our solar system. That discovery forced the astronomical community to accept that supermassive black holes exist. It was the quasar revolution. Today, we are living through the second revolution. Just as the discovery of quasars forced us to accept that supermassive black holes are real, the James Webb Space Telescope is now forcing us to confront a far more unsettling question. These cosmic titans did not grow slowly over billions of years, as we believed. Some of them were already giants when the universe was still in its infancy, and we do not yet fully understand how. In Part 1, we laid the foundation. We defined what a black hole is. We walked through the mathematics of the Eddington limit, and we confronted the too big, too fast problem, the discovery that the James Webb Space Telescope has found supermassive black holes in the infant universe that are simply too massive to have grown from small seeds in the time available. We ended with a promise that in May 2026, a team of astronomers published a result in the journal Nature that may have changed everything. A direct mass measurement of a black hole so dominant, so disproportionate to its surroundings, that it appears to have formed before its galaxy ever existed. This is the story of that measurement and what it means for our understanding of how the universe built itself. The object is called Able 2744-QS01. Astronomers simply call it QS01. It is classified as a little red dot, one of those compact, intensely red sources that JWST has been uncovering across the early universe. Spectroscopic observations place QS01 at a cosmological redshift of 7.04, which means the light we are detecting left this object when the universe was only 700 million years old. That is roughly 5% of the universe's current age. The look-back time is approximately 13.1 billion years. When this light began its journey, there were no spiral galaxies, no solar systems, no planets. The cosmos was still assembling its first large-scale structures out of hydrogen, helium, and darkness. Despite its immense distance, QS01 is physically tiny. The entire emitting region spans only about 1,300 light-years across. For comparison, the Milky Way stretches over 100,000 light-years. Normally, resolving a structure that small would be impossible, but nature provided an advantage. QS01 sits directly behind a massive foreground galaxy cluster called Able 2744, also known as Pandora's cluster. Able 2744 is a colossal gravitational structure, and its combined gravitational field warps the fabric of space-time around it. This warping bends and magnifies the light of objects behind it, a process known as gravitational lensing. The lensing effect is so strong that QS01 is not seen once, but 3 times. The brightest of these images, QS01-A, is magnified by a factor of over 6. Without this gravitational assist, QS01 would have remained invisible. Understanding what it actually is required a different kind of observation. To probe the dynamics inside QS01, the team turned to the Near-Infrared Spectrograph Integral Field Unit aboard the James Webb Space Telescope. Instead of capturing one spectrum of the whole object, it optically slices the field of view into a microscopic grid of individual spatial pixels, called spaxels. Each spaxel captures its own independent spectrum. The result is a 3-dimensional data cube. Because shifts in wavelength correspond to velocity through the Doppler effect, this data cube becomes a velocity map. It tells you exactly how every piece of the object is moving. By isolating the broad hydrogen emission lines, they mapped the velocity of the gas swirling around the core of QS01. The gas closest to the center was moving at extreme speeds, following a very specific mathematical pattern. That pattern is called Keplerian rotation. It dictates that orbital velocity decreases with the square root of distance from a central mass, the same law that governs the planets in our solar system. This is definitive mathematical proof that the overwhelming majority of the system's mass is concentrated at a single central point. That point is a supermassive black hole. The central supermassive black hole in QS01 has a directly measured mass of approximately 50 million solar masses, an object so massive that its event horizon would stretch nearly from the Sun to the orbit of Earth. But the raw mass is not the most disturbing part. In QS01, the black hole constitutes approximately 2/3 of the whole, 67% or more. The remaining third is almost entirely gas. In a typical galaxy like the Milky Way, the central black hole accounts for only 0.1% of the stellar mass. In QS01, the relationship is completely inverted. The black hole is the galaxy. The chemical fingerprints confirm that QS01 exists in an incredibly pristine environment. The gas surrounding the black hole is composed almost entirely of pure hydrogen and helium. Heavy elements are only manufactured in the furnaces of stars. Their near-total absence means that QS01 is an ancient system observed when very few stars had ever lived or died in its vicinity. The implication is inescapable. A 50 million solar mass black hole has no business existing in such an environment. It was not grown from a small stellar remnant. It was born big. At a redshift of 7.04, the universe was only 700 million years old. Even with maximum rate accretion, there is not enough time to grow a small stellar seed to 50 million solar masses. This points toward the direct collapse model, where a massive cloud of gas undergoes a catastrophic, monolithic gravitational collapse, forming a massive seed black hole in a single event. No intermediate stellar phase. The black hole in QS01 formed before its host galaxy. It sits as a gravitational anchor in the early universe, a naked engine around which a future galaxy has only barely begun to assemble. Roberto Maiolino, lead astrophysicist at Cambridge, described the result with no ambiguity. This is a remarkable finding. It is a paradigm shift in how black holes form and grow. Ignace Uojbalis put it even more directly. It seems that we have found a black hole that does not have a substantial host galaxy and that has predated stellar processes. This is evidence for primordial or direct collapse black holes. Francesco de Eugenio emphasized that before now, all mass measurements in the early universe were indirect, based on assumptions from the local universe. We didn't know if those assumptions really applied. The reaction was widespread. Priyamvada Natarajan at Yale observed that nature makes black hole seeds many ways. Fabio Pacucci noted that if little red dots contain black holes, they are enormous for such small galaxies. The publication triggered a coordinated pivot in observational strategy. Researchers are now aggressively analyzing other little red dots to determine if the black hole first pathway was the dominant mechanism for early structure formation. Before JWST, our understanding was limited. Hubble hit a hard wall at roughly redshift 11. Beyond that lay the cosmic dark ages and the cosmic dawn, an entire window that was essentially uncharted. Astronomers knew that a phase transition called the epoch of ionization had occurred when the opaque fog of neutral hydrogen that filled the early cosmos was rendered transparent, but the sources were debated. JWST shattered those models almost immediately. It discovered galaxies at extreme redshifts that are vastly more massive than any model anticipated, like JADES-GS-Z14-0, which existed a mere 300 million years after the Big Bang. It was also assumed that early galaxies would be chaotic blobs, yet JWST and ALMA have observed highly organized, smoothly rotating disk galaxies remarkably early, features predicted to take billions of years to develop. Even the chemical composition has defied expectations. Observations have revealed surprisingly high abundances of heavy elements, like oxygen and carbon, implying multiple generations of stars had already lived and died. The first billion years were not a slow process. They were fast, efficient, and violent. Galaxies formed more quickly, and supermassive black holes appear to have been among the very first large structures to exist. Where does all of this lead? The honest answer is that we are standing at the beginning of a revolution, not the end of one. The QS01 result is a single, extraordinary data point. It supports the heavy seed formation pathway, but the next critical step is to determine whether QS01 is representative or anomalous. JWST will continue to observe, but future observatories are already on the horizon. The Habitable Worlds Observatory and the Extremely Large Telescope will provide follow-up at resolutions that even JWST cannot match. And in the gravitational wave domain, LISA will detect the low-frequency gravitational waves produced by emerging supermassive black holes at high redshift, offering an entirely independent method of measuring their masses and mapping their growth histories. Closer to the present, the Event Horizon Telescope continues to sharpen our understanding. Its images of M87 star and Sagittarius A star gave humanity its first direct views of black hole shadows. There is a historical echo in all of this. In 1963, the astronomer Martin Schmidt sat at Palomar Observatory and analyzed the optical spectrum of a peculiar star-like object called 3C273. It was a quasar, a quasi-stellar radio source. That discovery forced the astronomical community to accept, for the first time, that supermassive black holes actually exist. It was a paradigm shift that rewrote our understanding of the universe. Today, we are living through the second revolution. The James Webb Space Telescope is forcing us to confront something arguably more profound. These cosmic titans did not grow slowly over billions of years. The universe, it turns out, did not build itself the way we expected. It built its most massive engines first and constructed everything else around them. The architects came before the architecture.